So welcome back to the lecture Biological Wastewater Treatment Plant. Today we will talk a little bit about the design of wastewater treatment plants. Especially we will go ahead with a statical approach. In the next lectures we will have also the idea of the German design state-of-the-art norms, and we will talk about dynamic modeling with the activated sludge model number 1. Okay, I will go away for a while, and finally what we need to know if we want to design a wastewater treatment plant. Also finally what you need to know, you need to collect data of the basic data of the effluent standards. Now you have to evaluate basic data and maybe future changes. Also in Germany, in some regions, the population decreases, and other booming towns, there increases. Finally, you also have to select appropriate processes and combinations for wastewater and sludge treatment. Finally, you have to design the perspective processes. You maybe have to do also a detailed design of construction and equipment. Finally you have to make a site surveillance, also the control if everything works fine. Also this is also important in many countries. If you are designed that, for example, the aeration tanks should be 6 meters deep, and they are only making 2 meters deep, and if there is sludge inside you don't see anything, then you have problems in the effluent. And a very important step is guidance and start-up and operation. You need here as well stuff that is able to operate proper. Finally you need to have knowledge over the overall system as well, about the sewerage system, the rainwater collection, treatment, storage tanks, and so on, and also of the receiving waters. It's good to have an overview over the whole range of processes and combinations. And of course you need to know about the advantages and disadvantages of processes, designs and equipment. And maybe you have also to make a balance between investment and operation costs. Important the considerations of future developments. Also nowadays many wastewater treatment plants has to set up a fourth stage for the elimination of micropollutants and microplastic. Therefore you need maybe place for extensions. Finally you need also do some consideration on demands. Also you are working always in different lanes, at least 2 lanes every in duplication. If you have to replace something or go in revision mode, then you don't have to switch off all the wastewater treatment plant. Therefore normally you have different lanes that one is always, or a few are always in operation. You have also to care about emissions of odor and noise. If you are operating a wastewater treatment plants, the neighbors will complain about of odor and maybe noise, even though there is no odor. And you have also maybe operating under very extreme condition, freezing, also hot wastewater temperatures, over 30 degrees. You have nitrate formation. This is wrong. Maybe you have also water shortages, and finally some communication skills are required. Finally, if you start to design a wastewater or water system, you have to ask if there is a sewerage system existing. This is in many cases the case, at least in Central Europe. And then you have also to check if this system is working okay, or if there are maybe big renovation demands. And if you say yes, this is working, then you can go to the design of the wastewater treatment plant. Of course, you can then consider reuse options of the water. For example, we have here many water shortage regions, and there also good treated water has a price or a benefit. Yeah, if this is not the case, you can check if the sewage can be rehabilitated. Also finally, you have also to compare investment and operation costs, and then check if this is operational in future. If this is the case, you can also go to the design. Yeah? But if this is not the case, then you can also think about, even though if there is no sewerage system available, you can adapt to the situation. Also you can initiate rainwater infiltration if this is feasible. And where, if you are constructing over rock, this is difficult. Yeah, finally you have to have a look to future water availability and consumption. Sewerage system you have also to flush, and you need also water. You can think about decentralized systems, you can think about reuse-oriented wastewater treatment, and you can compare costs. Yeah, if there is sewerage is planned, then you can also go to the design. And if you say no, maybe you can design also decentral systems. Yeah, collection of basic data and effluent standards. Under this topic, it is also a difficult exercise to get data. You have here missing or unreliable data. They are not up to date or very few parameters. Also, the sewerage is sometimes an unknown labyrinth. You have also, if you are unlucky, infiltration. If you are very unlucky, infiltration of seawater, and you have maybe very heavy seasonal changes. In the Baltic Sea, for example, in Christmas, all the people are going to their holiday houses, and then you have a problem. And eating, of course, a lot of meat, and then you have problems with nitrogen. Okay, you have also to check what is going on. Also finally, you can check the water consumption due to the population. There are some experienced values, but you have also to consider the industry impact. But there you have also lists of the products and the resulting water consumption. Maybe you have data from the old wastewater treatment plant. You can make measurement campaigns. This is, in my opinion, a very good thing, but sometimes this is expensive. The people don't want to spend this money for cost, but you can also go to the population equivalents. Yeah, the future developments covers the population growth or industry. It will be moderned or changed to another form of industry. This has also some impact to the water consumption. City planning or unplanned development. Also this is always good to make a proper planning beforehand. And you have to see that there is a capacity of the sewerage systems in the way that's covered future situations. Sometimes if the sewerage system is too big and the time where the water stays in the sewerage system is too long, you have also problems. But finally, if the capacity is too low, then you have also to go ahead. Therefore, a stepwise construction with leave of space extensions is a wise area. Yes. Yeah, the population equivalent, this maybe changes also from area to area, but in Europe we have these main wastewater parameters, this so-called population equivalents, and all data from industries are also given more or less in this case as gram per person and day raw wastewater. There we have the BOD 60 grams, COD 120, suspended solid 70, total nitrogen 11, total phosphorus 1.8. And after primary sedimentation, normally we have a short form. You see that the solids are reduced, but the nitrogen and phosphorus really low. Yes. In any case, you have to think about the sludge treatment. The sludge normally is digested, and after digestion dewatered, and the water is also polluted, and sometimes 20% of the load is recycled. And if you are adding chemical precipitation, then maybe you remove more BOD and CSD and SS as well in the primary sedimentation if you are adding precipitants beforehand. Also this has to be checked and balanced before. We want to make a brief example of a quite simple wastewater treatment plant. We have here one population equivalent, more or less 150 liters per day. Every person consumes water and produces wastewater with a COD of 120 grams per day, and 11 and P and K we see here from the sketch. And if we make an example for 5,000 personnel equivalents, then we can calculate from this that we have 750 cubic meter per day of wastewater, and finally the 600 kilograms per day COD load ends up at a mean concentration of 800 grams per cubic meter COD, and this we can do for the N components and K components as well. And finally we have in the range of 73 grams ammonia N or organic N in the inflow, and 10 grams per cubic meter P and 20 grams per cubic meter potassium. Finally, besides the poor water flow, we also have to consider the hydraulic water flow. And if we have, assuming in this case, an only wastewater sewerage system, as separated, that the rainwater is not coming in, we have here to calculate with an hydraulic volume flow which is much higher, 2 times the inflow, which is quite normal for this case. Now we have here to think what parameters we are using normally. Also in Germany and in the Switzerland we have the 4 or 5 samples. Also this means for the collection we are collecting 5 samples, and 4 has to be under the control values. And finally you can imagine in 80% of the time we have to fulfill everything. This is a normal operation, and then sometimes we have exceptional conditions, and there also Versa control is required. Finally, to calculate our distribution of the values, we have to do some statistics. Also we are calculating from an ordered list our cumulative density function normally with this formula. Also this is at very small and very big values has no this big effect, and this factor 3 was figured out to be quite suitable for wastewater treatment. Normally you have an ordered list. Also finally in this case BOD is in German as well, but this means BOD 5 values. Also the smallest was 4.5 and the biggest 41. They are ordered, and then the density function is calculated with the index and the total number of 43 and comes up to this. Yes, and this are normally presented in this probability chart, where here the root of the logarithm is sketched. finally you can see this normally that 50% is in the middle, and very small and very high values are ending up to the end. And the special form is due to the normal distribution. If the values that you have follows the normal distribution, this would be a straight line, and if not, not. And finally, if you see here the circles, which are the linear form, you see this is not linear. And this you often have in wastewater treatment, that they don't follow the normal distribution. And therefore, normally you sketch it in a logarithmic scale, and then, okay, not perfect, but a lot better, it follows the normal distribution. They are normally logarithmic normal distributed. Yes, and to find out the 80 percentile, finally you have in this presentation as well the error of distribution, and depending on the numbers you are changing, if you have thousands of values, then you can pick out the value at 80%. But in this case we only have 154, and then we have to go a little bit higher. And then we go back and receiving this value of 9.4 milligrams. That means with 95% security, 80% of the values are below 9.4 milligrams per liter. Finally, as an operator, you want to be more or less sure that everything works fine out. Okay, the threshold of the EU directive is be 15 milligrams per liter, and then you are quite fine. Also quite sure that everything is okay. Another thing is in hypograph. Also here is for 1 year given many flow rates, I think every 15 minutes, and there you see you have a high variety. And if you go to the top and say, yes, we want to have be sure that in this case 5 cubic meters per second, unfortunately there is no unit, then we are safe. This is true, but finally you need a very, very big volume. Nobody would like to pay this. And how to get better information out of this data? You can maybe make an special mean value, a floating mean value, which covers more time. Also this were 2 hours samples of the volume flow rate, and the wastewater treatment plants, the water have a main retention time of around about 24 hours. That means if you have for 2 hours very high inflow rates, this has not this big effect. And therefore we are making this mean value over 12 values and putting this as an inflow value. And there you see, yes, there are still some fluctuations, but they are in the range between 1 and 1.8 cubic meters per second. And there you can arrange this a little bit. This information you can get out. Also this is called rolling mean. Also finally that you have always 12 values considered, which was before the place when you are here. You can also sort these values to the daytime. Also finally there are values between midnight and 2 o'clock, and then 2 o'clock 4, and so on. You can form the mean of these intervals. And then you see, yes, you have also fluctuations during the day. And okay, here is the confidential interval given, because there are many. This is quite small. But if you know, okay, at 4 o'clock there is everything quiet, and then at 6 the water comes to the wastewater treatment plant, maybe with a load, then you can in advance switch on the aerators and so on. There you have this additional information, and as well the total mean value. Also this you can also extract from your data. The control value, how are the control values are taken, is also of some importance. In many countries there is a 24 hours mean value that has to be undergo. In Germany there is this qualified sampling method. That means within 2 hours there are taken 5 samples and 4 has to be below the control value. And the EU wants to make everything more or less uniform, and so the Germans say no, we are more strict. But here is an example, this is not the case. Also finally there was taken 2 hours mean values over 1 week, and every day there were taken 2 qualified samplings, and from this value of the 2 hours mean value the 24 hours mean values are calculated. And then this is also brought in this nice probability diagram, and with respect to the number of samplings the 80% value was compiled. And finally, if you only have 7 values, then you have to go also to higher numbers to be sure about the distribution. Nevertheless, it came up that for the qualified sampling procedure there was a mean value of 2.6 milligrams per liter, a control value. That means in 80% of the cases the value of 2.9 milligrams per liter N was reached with 95% security, and for the 24 mean hours the value was 4.9 milligrams per liter, and for the 2 hours mixing probes samples it was 5.1 milligrams per liter. Also the qualified sampling was far below. Now, this was very surprising because everybody expected this is more strict, but the reason you see here, where over the time the dates are given, this is because the sampling method was not really professional. This was always done in the morning, also after breakfast and before lunch. But the peaks are coming always more or less at midnight. And so you have to also make this an everyday, as you go there at midnight, you go there randomly to take the samples to get a good example. I'm a fan of 24 mean values, 24 hours mean values, because this represents the emission to the receiving water body the best. Finally, the next thing is we have to specify what quality we need. Also there we say we have 100 grams per cubic meter COD, less than 2 grams per cubic meter ammonia N. Total N should be below 18 and P below 1 gram per cubic meter. And then we go through the wastewater treatment plant. This mechanical treatment is not part of this lecture, but finally you have the screenings, and finally you make sievings. You make this from the catalog, from experience. They gave you data and how many cubic meters are passing, and from this you have also different lanes. Normally they are always over-dimensioned. Then the main challenge is to find out the mean sludge retention time which is required for this operation. Also we have here learned that this sludge retention time in average conditions that's the same sludge produced as that we can remove from the system. And finally, under stationary conditions or mean conditions, the sludge that is leaving the system is the flow multiplied with the concentrations in the effluent and the excess sludge flow rate and concentration. The sludge retention time is defined as this equation, which is also the same as the sludge production with respect to the sludge concentration in the system. We have to have a look to the applicable process. Finally, we have here more than 18 gram nitrogen in the influent. Therefore, we need also a process with denitrification. We want to have a look to the activated sludge process with pre-denitrification, and maybe an activated sludge process for denitrification and a trickling filter for nitrification. We can use also other processes, but we will consider this. The activated sludge process with pre-connected denitrification. There we have the inflow coming in, we have our denitrifying reactor, then the water comes to the nitrifying basin, which we aerated. Yes, of course, we have to recycle sludge, and we have our return sludge flow, and we need also a clarifier with a special clarifier surface to separate all the sludges, and we are removing excess sludge. Everything which is red, we don't know yet. We are assuming other concentrations, other rates from experience or what is possible. First of all, we need to find out our sludge retention time. And there we have a look to the autotrophic microorganism. We have here already learned that the growth rate and the sludge retention times are bound together. And so we are using the reciprocal of the growth rate for nitrificants at the temperature of 15 degrees with low oxygen concentration and low ammonia concentration. Then we have a temperature compensing term if the temperatures are different from 15. We need a longer, higher sludge age if the temperature is smaller. In Germany, normally the design is made for 12 degrees centigrade. And we have a safety factor, which depends also on the fluctuations and also on the dimensioning of the wastewater treatment plant. Now we go to some assumptions. We have a look to the dry matter concentration. We have here a wastewater treatment plant here with pre-treatment, primary sedimentation and grid chamber and everything, which is beforehand. And what we can achieve in the sludge, in the aerated basins, is in the range of 3 kilograms per cubic meter sludge. We're making this for the design temperature of 15 degrees centigrade. Because we have a small wastewater treatment plant, we have a quite high safety factor. Now in the new regulation this is process factor, but the safety factor was in the range of 1.2 until 1.7 depending on the size. Hamburg wastewater treatment have 5,000 kilometer sewerage systems, and there the water is coming more or less uniform, and they have the safety factor of 1.2. But here we have a small settlement or something like this, there we can use it a little bit higher. Then we're calculating the sludge, excess sludge production. We make this very raw. We know what COD has to be removed. The Q in minus C in minus C out. And we are putting the yield coefficient. And this is 750 cubic meter times 0.7 kilograms per cubic meter times 0.4 kilogram dry matter per kilogram COD. And then this is resulting in 210 kilograms per day. We will see that the yield coefficient depends very much on the units. what you are putting as a measure for biomass or for COD, but finally this is in this range. If you are measuring the dry mass as well as COD, then this is 1.25 or 1.33 times higher, and then this value becomes higher as well. Or if you're using here TOC, then of course this is smaller. But anyhow, if you go on based on COD and dry matter, this is in this range 0.4 to 0.5. Yeah, with this information we can calculate our sludge retention time, which is here from our aerated volume for nitrification. We have here our concentration given, we have our volume and what sludge we are producing. We can rearrange these equations, and this is ending up in 400 cubic meters. So finally we are calculating 5.8 days sludge retention time. We have this sludge production rate of 210 kilograms per day, and we can operate the reactor with 3 kilograms per cubic meter. This is resulting in 400 cubic meters. Yeah, for the denitrifying volume or the total volume, we are assuming that the denitrifying volume is between 0.25 to 0.5. In reality, this is often 0.5, but we are choosing here 0, also 1/3. And then we have 600 cubic meter nitrification, 200 cubic meter denitrification, and the total volume, the total volume is 600, 200 denitrification, 400 nitrification. Yeah, normally you are starting always in this form, maybe with a little bit more precise formulas, but then you are proving if the COD is sufficient for makes the denitrification in this volume, and adapting this volume. This you will see how this is working in another lecture, but more or less the idea is the same, but you're making here a finer adjustment. Yeah. If you have the volumes, then you need to know what internal flow rates you need. Also finally, first you have to define what degree of denitrification you need. And there you're calculating what is the nitrogen that is allowed in the effluent, and what is the nitrogen in the influent. And finally you see that you have to have more or less 77% denitrification. You can say, okay, we have here also a few milligrams of ammonia, but finally some nitrogen is also used for the cell growth, also the assimilation. If you don't have any autotrophic bacteria for denitrification in the system, you will also reduce ammonia, but not really far, only what the biomass is building in their cell mass. Yeah, then we are assuming that we have a very good denitrification. All nitrate that enters our denitrification reactor, as they are mixed with fresh wastewater, will also disappear, will be reduced to N2. And finally, the best thing is this: if we return everything, then we have no effluent. Yeah, but finally, you can end up to this formula: only what you are recycling and bringing back with the return sludge. With respect to the total flow, you can denitrify. Yeah, and then we are assuming that our return sludge flow is the same as the inflow, also the return sludge rate 1. Normally you are operating between 0.5 and 1, also bigger than 1 is very unusual, because finally this is too much mixing, and if we are doing so, we can calculate from this the recirculation volume flow, which is 3.5 higher than the inflow rate. And the clarifier, we know that we have maximum surface flow rate of 50 cubic meters per square meter and day. This is in the range of 2 meters per hour. And we have also to calculate the hydraulic flow to the, also the peak flows and the hydraulic flow to the clarifier. And there we have here seen we are calculating with the hydraulic inflow of 2 times Q in, and the return sludge flow is also clarified. Also this 3 times Q in is used in the clarifier. There we have 2250 cubic meters per day, and with the surface flow rate, the maximum loading rate with 50 cubic meters per square meter and day, this ends up in 45 square meter. And if it's 4 meter deep, then we have here 180 cubic meters or something like this. Okay, if we can do this a little bit different, we can here also do the denitrification beforehand. And then we have a biofilm reactor. Also we will talk in future lectures very intensive as well about biofilm reactors, and bring the water back. And can we save or have some synergies? Also finally the internal flow rates we have to calculate. We don't have a return sludge. Therefore this is one higher, 3.35. Also finally the same considerations as before. But we don't have a return sludge with nitrogen. Also therefore all this material comes from this. Also here we don't have nitrification. There's no nitrate inside. Then we can calculate the sludge retention time, but now we have to have a look. Also this is wrong, not to the nitrificants. This has to be changed. I will do this. This is for the heterotrophic microorganism. They have higher growth rates. They are growing faster, but also for small concentrations. We have the same safety factors and temperature compensing area. We are producing, in this case, more or less the same amount. We are saying, okay, in this step we are degrading the COD, in the next step the ammonia. Therefore we are coming up to the same considerations as beforehand. Also we are producing 210 kilograms per day sludge. And this ends up in another reactor volume. Also if we are calculating this, we have a higher sludge retention time, smaller, also higher growth rate, resulting up a little bit less than 2 days. Before it was nearly 6 days, and therefore we have a smaller volume of 130 cubic meters. Also we had estimated 200 for denitrification beforehand. Then we have to have a look to the hydraulic rate. Also finally this is clarification in between. There we don't need 100% particle-free water. Therefore we can allow a higher surface loading rate. In this case 100 cubic meters per square meter and day. Also double 4 meters an hour, more or less. But we have also a higher recirculation. Here we have 2 times Q in is the hydraulic load. We have the return sludge that we bring back from the clarifier, and we have the recirculation rate. Assuming we have a return sludge also 1, and this ends up in 4,750 cubic meters per day, and also 48 square meters. Also more or less as a normal clarifier we had before. Then we have a look to the nitrification inside the trickling filter. There we know that we have a surface uptake rate of 30 milligrams per square meter an hour, and at 15 degrees. And then we can calculate, also in our case for 15 degrees, we have this 30. We are assuming we have a high-tech packing material which provides us with 200 square meter per cubic meter and day. And from this we can calculate the volumetric nitrification rate by multiplying the surface depending nitrification rate with a specific surface and bringing this also to the unit day. Then we are coming to 144 grams per cubic meter and day. Also finally, for biofilm processes, you can make in the lab experiments how much substrate you can uptake with respect to 1 square meter. And then you have a value with respect to the surface, and you can then compile from this the uptake rate. Yeah, finally, in this case, if we know what would be the uptake rate, we can calculate if we, assuming we want to reduce everything, the inflow is here minus the uptake rate multiplied with the volume should be 0, and compiling this in this form, we can calculate the volume of the trickling filter. We have here the 750 cubic meters, the 33 grams and 144 grams per cubic meter a day, ends up at 380 cubic meters. Also nearly the same as we had in our activated sludge process with 400. And we need here, unfortunately, a final clarifier. There we have to put as well this 50 cubic meters per square meter a day, the surface flow rate, and we are designing the peak flow 2 times Q in, and this ends up in 30 cubic meters. Yeah, finally we see we have more or less the same dimensions, and we have here to decide what is more process stable or what not. Yeah, I will go back to a very simple approach, an old approach from the very beginning, a typical civil engineering approach, that there are observed many plants and then the conclusions are put. Also finally, the idea is the food biomass ratio, and this is mainly done based on BWD5. Also finally, the BWD5 load is put in respect of the volume and biomass in the aeration tanks. Yeah. Also this is the sludge loading rate in kilogram BOD per kilogram suspended solids and day. And you can imagine if you have a lot of mice and a little cheese, then if you put more cheese, then the cheese consumption rate will grow. But if you put more mice, the cheese will not disappear faster. But in this case, if you have a lot of cheese, the cheese is degraded slowly, and if you put more mice, then this goes faster. So therefore you need a special relation to have less concentration. And in this stage there is observed for different temperatures many wastewater treatment plants in Central Europe, and the elimination efficiency with respect to BWD5 is sketched. And there you see if this is smaller than 1 kilogram per kilogram TS, or kilogram BOD per kilogram S, then this is quite high. And here this is really high. And from this there's a data, also 0.3 is compiled. If you want to have stable BOD removal, there you have also some reserve, or 0.05 if you also want to have stable nitrification. Also these are the edge marks, also typical values: 0.3 kilogram BOD5 per kilogram suspended solids for BOD elimination, 0.15 kilograms BOD per kilogram SS a day for nitrification. And if you go 3 times smaller, 0.05 kilograms BOD per kilogram suspended solids, you have also simultaneous stabilization. That means that the sludge that you are removed from the system don't digest anymore. You can dewater it directly and use it. Also, therefore, this is only done in small wastewater treatment plants, maybe in rural areas where you don't have this sludge treatment possibilities. Yeah, sludge concentrations that you have typically in the aeration tanks, this is 3 kilograms suspended solids if you have a primary clarifier, or if you are adding some iron or aluminium salts for the precipitation, then you have here in the range of 3.5 kilograms suspended solids. And if you work without primary clarifier, for example, if you want to make a simultaneous stabilization, you are ending up in the range of 4.5 kilograms per hour. And you have this hydraulic retention times, more 18 hours than 3. Finally, to calculate this, if you want to have nitrification, you are choosing the 0.15 kilogram BOD per kilogram TSS a day, assuming 300 grams per cubic meter BOD, also 600 grams per cubic meter COD, half-half, and 3 kilograms TSS. What hydraulic retention time in the aeration tank is resulting. Finally, this is the reactor volume due to the inflow rate. And there you have here to calculate what tank volume. And this here I can rearrange the equation for BTS. And then you have this 750 cubic meters, this 300 kilograms per day per cubic meter BOD, and divided by 0.05 kilograms BOD per kilogram TS a day, and 3 kilograms TSS per cubic meter. This ends up in 500 cubic meters. And then you have the inflow rate and the volume, and this ends up in 16 hours hydraulic retention time. You see also with this very brutal, crude approach, you are ending up to more or less the same result. This is always sometimes a good proof if your calculations is in the dimension okay, or if you make further calculations with dynamic modeling or what else, you need here a point to start, and then you see maybe you can make it smaller or not. And therefore this is a quite good thing for engineering to have with a table calculator, very easy one idea. Okay, hopefully you have got it. Thank you very much.